This video will cover Section 4.6, Graphs of Other Trigonometric Functions, and it is for the class Math 2412, Pre-Calculus 2. In this section, we are going to have the following objectives: sketch the graphs of the other trigonometric functions that we haven't learned how to graph yet. And so that will be the tangent function, which we have here. Then we will have the reciprocal of tangent, which is cotangent. And then finally, the other two will be secant and cosecant. So I want to remind you that cosecant, let's say cosecant x is the same as the reciprocal of sine. And so we're going to be reviewing the graph of sine and then learning how to graph the reciprocal of that. For secant, we will be using the graph of cosine. In fact, the reciprocal of cosine, because that is how secant is defined to be. And just to remind you of the quotient identities, we have that tangent is equal to the quotient or the ratio between sine and cosine, and cotangent happens to be the reciprocal of tangent, or we could also say the reciprocal of the quotient identity for tangent. So that would be cosine x over sine x. From our previous section, we learned how sine is an odd function, and because of that, it is symmetric with respect to the origin. And the fact that it is odd, it means that if we were to substitute x with a negative x, we wouldn't get the same as sine of x, but the opposite of sine of positive x. Then we have our even function, which is cosine. And so for cosine x, if we were to substitute x with a negative x, we will get the exact same as the original function. So that is the difference. Now, based on that, we're going to use those two. We will be using sine of negative x, sine of negative cosine x to see if tangent will be odd or even. And I know the answer is already here. It is odd, but let's see why. So we already know, and I know I keep writing it, but it's okay. Sine of x divided by cosine x. That is one of the quotient identities. So if I wanted to rewrite tangent of negative x, and then that will give me sine of negative x divided by cosine of negative x, which is what I have highlighted up here. So now, because sine is an odd function, I'm going to replace that with negative sine of x of positive x. And because cosine is an even function, I'm going to replace that with cosine of positive x. Now, when you divide a negative by a positive, you are going to get a negative. And so this turns into negative tangent of positive x. And that is exactly what we were trying to get here. And this is what we started with. So that is a way to prove something called an identities. We will do more of this in section, I believe it's 5.1. So because the tangent function is odd, we know that it is going to be symmetric with respect to the origin. And functions that are symmetric with respect to the origin, for example, the cubic function and the tangent function, it actually happens to be very similar to it, and it is like several of those cubic functions. Now, side of that, we're going to have this that is actually very important, and they are certain values that we will have to exclude from our domain, and those values are going to be called they're actually going to be vertical asymptotes, because the function of tangent is not defined for those values. How do we find those values? Well, those are going to come from the undefined tangent, the angle measurements for which the tangent is undefined. And so that will occur anytime that the cosine is equal to 0. Because if we divide by 0, we will get an undefined solution. So that happens, and I'm gonna just draw here a unit circle at the points pi over 2. If this is the unit circle, that will be pi over 2, because the coordinates of that unit at that point on the unit circle will be 0, 1, meaning that the cosine value is 0. So tangent is undefined at pi over 2, and also it's going to be undefined down here at 3 pi over 2, because the coordinates at that point with respect to the unit circle are 0, -1. And so remember, anytime the cosine is equal to 0, then our tangent is undefined. Also, it is important to notice that the approximation for pi over 2 is going to be plus minus, well, of course, we're looking at, okay, so let's do the following. For this angle, we're going to consider that to be pi over 2. And then so we can get what's happening on the left and the right side, we could think of this angle in going in the negative direction, so it will be negative pi over 2. So that is what we see here. So the tangent is also undefined at negative pi over 2, also at 3 pi over 2, but also at positive pi over 2. So what is exactly in between? And that will be 0. So let's go ahead and trace an x and y axis. Not as good as I want it to be. Okay, let me try this again. No. Okay, so we have the origin here, and we know that the tangent at 0 is at 0 radians. It is exactly if we use the points, the coordinates of a point, it will be at that point, the coordinates will be 1, 0. So if tangent is sine over cosine and sine is 0, then tangent at 0, it will be at 0 radians. It will be 0 over 1, which is equal to 0. So that is why we have here for 0, if x is 0, tangent of 0 is 0. And that's what we're going to use as our x-intercept. However, this graph is going to have several x-intercepts. So now I'm gonna go ahead and label my x-axis. So I'm gonna place my pi over 2 here. And here we will have positive pi over 2. So I'm gonna rewrite this part. And this should be negative. So at those 2 points, we are going to place our vertical asymptotes because the function is undefined there. Now, if I go another pi over 2 units on the right direction, that is going to be pi. Now, is tangent defined at pi? So here at this point, I'm going back to the unit circle that I have. At this point here, the one that I'm marking with purple, that is pi, right? So the coordinates at that point with respect to the unit circle are -1, 0. And so the tangent of pi is going to be sine over cosine. The sine is 0. The cosine is -1. So 0 divided by -1 is 0. So if I want to graph that point, it will also be an x-intercept. Okay, now sorry about that. Okay, so if we go back to the unit circle, actually, I'm just going to draw a new one here. Let's see. So we have that. Now, let's see what will happen if we go another pi over 2 units to the right. So that's going to be 3 pi over 2. And at 3 pi over 2, the coordinates of that point will be 0, -1. So to find the tangent at 3 pi over 2, we will need the sine at 3 pi over 2, which is -1, and then divided by cosine, which is 0. So at that point, it's going to be undefined as well. So we will have another vertical asymptote. Now, if we want to know what will happen on this side, so for -pi in the negative direction, we start here at the positive x-axis, but we go in the clockwise direction this way. So -pi looks the same. It's actually placed in the same place as positive pi. So at that point, the sine and the cosine are -1, 0. So the tangent at -pi or at pi is going to be 0 over -1, which means it's going to be 0. So we have it right there. And if we were to do the same thing to figure out what will happen at -3 pi over 2, we will also get an undefined answer, and that will be another vertical asymptote. And just quickly, I want to clarify this with you guys because I don't want any confusions, but anytime that you have a number such as, let's say, 7 divided by 0, is going to be undefined. Any number, it doesn't matter what number this is. Now, if you have 0 divided by a number, is always going to be 0. And in fact, we could just say equals 0. When things are undefined, we don't say they equal undefined. They are undefined. So we use the word is. And in this case, they will always equal 0. So it doesn't matter if it's a negative number on the denominator, as long as the numerator is 0, this will be 0. Okay, so One way to remember this is that if you have any number divided by 0 is a big no if you read it vertically. So it is undefined. I call those big no-nos. But if you have a 0 on the numerator divided by any number, let's call it k, that is okay, because that just equals 0. So 0 on top is okay, 0 on the bottom is a big no. And I want you to think, what do you think 0 over 0 will be divided? I mean, if you divide it, what would you get? Would you get undefined? Would you get 0? Or would you get a 1? I want you to think that for our next live session. So let's go back to this graph, and I'm gonna erase or delete some stuff here to make room for our curves. Okay, so, oh no, I lost my x-axis. Okay, we have it back. So what's gonna happen now is that, let's say that if we were to plot this point right here, or this point right here, they will be somewhere, let's say here, and this is just an approximation. Okay. And then if we get closer to 1.57, because if you recall, pi over 2 is approximately 1.5708. So in fact, let me write it here, 1.5708. So 1.57, it's closer to pi over 2 than 1.5 was. However, if you look at the y values, they are increasing rapidly. So we go from 14 to 1,255, and just a difference of 0.07 from the radians. So what that implies is that as we get close, as x approaches pi over 2 from the right, so we put a plus here, a tangent of x approaches infinity. And for that reason, when we trace our graphs, they will look like that. And then on the left side, what's happening? So as x approaches negative pi over 2 from the left, tangent of x is approaching negative infinity. And so the closer you get to pi over 2, the more negative it gets, I guess. It approaches negative infinity. And it will never touch the vertical asymptotes, which are happening at pi over 2 and negative pi over 2. Now, what happens between every set of asymptotes? Well, same behavior. So this will just be repeating. So you could see that if you remember, the period for sine and cosine is 2 pi, meaning that the behavior of the graph repeats every 2 pi radians. With tangent, it's not 2 pi. It's something smaller. So I want you to think about that. And if you're not sure, I want you to calculate the distance between negative pi over 2 and pi over 2. And that will tell you the period. So the period, in case you don't know yet, is going to be pi. So the behavior of the graph of the function will repeat every pi units or radians. So the same thing that I did here with the arrow notation as x approaches pi over 2. So tangent, another way to say that tangent goes to infinity is to say tangent increases without bound. Okay, and oh, this is wrong. I should have done a set from the left, so this should have a minus because we're approaching from the left. If we're looking at this side of the graph, we're on the left side of the asymptote. So sorry about that. And so the other one should be from the right. Yes. And because we're approaching negative pi over 2 from the right side of the asymptote. Okay, so we made that correction. That was from the left, this one. This is from the left side of the asymptote. And the other one is from the right side of the asymptote, but the other asymptote, negative pi over 2. And in that case, we say that tangent of x decreases without bound. That's another way for us to say it approaches negative infinity. So we have here the parent function of the tangent function, y equals tangent of x. And as we discussed already, the period is pi. And that tells us that all the behavior will repeat every pi units. So if we started with an x-intercept here at the origin at 0, 0, at pi comma 0, we'll have another x-intercept. And just so you know, if we were to extend this, our next intercept will happen exactly at 2 pi. That will be another x-intercept. And we could just mark it here. And if we were to go in the negative direction, our next x-intercept will be the one that occurs right here. And I cannot draw for some reason. And that will be, oh, actually I skipped this one here, negative pi. And then the next one will be negative 2 pi. Okay, now the domain is going to be all of the real numbers. So the angle could be anything except those angles that will cause tangent to be undefined. And for those are going to be the the one where we have our asymptotes. And you could see here for domain, we use the does not equal sign, but for asymptotes, we use the equal sign. So it will be at pi over 2, as you could see. They will also be at, so that's why we have to exclude them from the domain. So it will be here at pi over 2, at negative pi over 2, and also at any other multiple of if we were to add pi over 2 plus a multiple of pi. Remember, the period is pi, so it makes sense that the behavior happens every pi units. So for example, the asymptote from here at 3 pi over 2, you could also calculate it by adding pi over 2. You let this n equal to 1, so that means that we're just adding 1 times pi, and that will be pi over 2 plus 2 pi over 2, which will be 3 pi over 2. And that is the asymptote that we could see right here. We have another one here at negative 3 pi over 2. And they just keep happening just like that. Okay, and the range in this case, with sine and cosine, the range was limited, very limited, from negative 1 to 1. But for tangent, the range is actually all real numbers, all of them. And symmetry, again, is going to come from the origin. And let's just remember that tangent is an odd function. And we could also check that by, for example, if we go back to this one, you could see that the tangent here at negative 1.5 is not the same as the tangent of, in this case, it's negative 14. So it's not the same as the tangent of positive 1.5. It's actually the opposite because the tangent of 1.5 is positive and this one is negative. So it's going to be the opposite of the other tangent, the one that we have here, or we could also write it in this way. The negative tangent of 1.5. That's what it is. So we already discussed where the vertical asymptotes are going to occur. And also we discussed what we need to do for the domain. We have to exclude those places where the asymptotes will be located at. And then also to sketch the function, we're going to use the same idea that we use with function transformations. So for example, the A here, it will represent a vertical stretch. And then the constant here, B, it will represent a vertical, and I'm sorry, not only stretch, but stretch or shrinking, stretching or shrinking. The B will represent a horizontal stretching or shrinking. And then we have C, which will represent a horizontal shifting, or we also call it translation. And just like we did with the previous section, we're going to learn how to locate certain key points such as the intercepts and the asymptotes so that we could graph our tangent function. Just like we did on our previous section, we are going to create two equations using what we will have in here inside the parentheses, which is what will represent our input. Well, our input is x, but that will be what we will use to calculate the tangent. And so we're going to do that to locate the first two consecutive vertical asymptotes. And with the parent function, we started discussing how the vertical asymptotes occur at pi over 2 and negative pi over 2 because tangent is undefined for those two angles. And because of that, we use those two for the equation. When we discuss sine and cosine, we were using bx plus c or minus c equaling to 0 and bx minus c equaling to 2 pi because that was our ending and our starting point in the case of sine. In the case of cosine, there were either R2 max or R2 min. So let me just write it down. We use these two equations with sine function and cosine function. We did it with sine function to find the intercepts or our starting and ending point, which typically are x-intercepts unless there's a vertical shift. And then with cosine, we did that to figure out where our maximum or minimum points were going to be located at. So for tangent, we are concerned about those two equations to find two consecutive vertical asymptotes. That's what they're. The amplitude of the tangent function is not defined. And what we're going to do is after plotting the asymptotes and the x-intercepts, you could look up some other values. You could use your calculator. That's perfectly fine with me to plot a few additional points between the two asymptotes and sketch one cycle. So one cycle will be what we graph between pi. I mean, something with a period of pi. So if the asymptote here is negative pi over 2 and the other asymptote from here is positive pi over 2, then remember the distance from here to here is pi, so because that's the period of the graph. And if you are doing this by hand, what you will do is figure out what is pi. I call this like the quarter points. So it will be, and they're located between the intercept and the asymptote if you notice. So that value will be at pi over 4, and then this one will be at negative pi over 4. So you could also use that to get some good points. and then trace your graph. So you can have 3 points, and that will allow you to have a better graph. After that, it says just here to sketch 1 or 2 additional cycles, you know, depending on what WebAssign is at or your exam is asking you to do. For example 1, we're going to sketch the graph of y equals tangent of x divided by 2. So this is what we're going to use to create our two equations. And remember, based on the parent function, the two consecutive asymptotes that happen to the left and the right side of the y-axis will be at negative pi over 2 on the left and then pi over 2 on the right. And so that's what we do from the previous slide. Remember, we say we're going to set that equal to those two values of the asymptote of the parent function. So with that, that will help us to find the asymptotes for our function transformation. So in this case, to solve for x, all I need to do is take this positive 2, which is dividing, take it across, and it's going to be doing the inverse operation, which is multiplication. Or you can think of it as we multiply by 2 both sides. And so if we do that, 2 divided by 2 is equal to 1, but we do have a negative, so this will be negative 1 pi. For the other equation, same thing, we take the 2. I'll do this example the other way. So you multiply by 2 on both sides so that you can cancel it. So x will equal to positive pi. So those two are our first vertical asymptotes. And so instead of being here at negative pi over 2 and at pi over 2, we're actually going to have them at negative pi and positive pi. And you can see that here it is undefined for those two values. So let's go ahead and trace those. Those are going to be, when you trace the tangent function on your WebAssign, you might have to make sure that your lines are dotted or dashed. So don't leave them solid because that will be wrong. They're not solid implies that it is part of the graph. The asymptote implies that it's not part of the graph. Now, if we were to substitute the values that we have in between, well, first of all, the asymptote will be 0 because the tangent of 0 divided by 2, and I do that because I'm using this equation, is equal to the tangent of 0, which is equal to 0. So we have the same x-intercept. So to know what's happening, let's find what's, to find another y value, let's go ahead and find the midpoint between the x-intercept that we have and the asymptote. So the midpoint is clearly pi over 2. So if we substitute pi over 2 here in place of this x, I'm going to write it down. So this will be tangent of pi over 2, but we're dividing by 2. And so that will be the tangent of pi over 4. And so the tangent of pi over 4, that is a pretty easy one, because remember sine and cosine at pi over 4 happen to be the same. The square root of 2 over 2, and for cosine and for sine is also square root of 2 over 2. So tangent is of pi over 4 is 1. So that will be, let's assume there's a 1 here, so that will be a point. And then for tangent of negative pi over 2, substitute it into this equation again, but we still need to divide by 2. And so that will be the same as tangent of negative pi over 4, which will be equal to negative 1. And that will be, if we assume negative 1 is here, we could be like a point right here. And remember, we did start with pi over 2, as you see here, or negative pi over 2. That's what we substituted in place of the x, but we still had to divide by 2 because that's how the equation was written. So that's why we ended up with a 4 here, okay? And so if we connect those points, It kind of looks like a cubic function. And then if for WebAssign or for your exam you need to graph more than one period, you will just repeat the same behavior. If the question was, what is the period for this function transformation? And this is the one I'm referring to. It wouldn't be the same period as the parent function. It will be bigger. And if you calculate the distance between negative pi and pi, that is actually 2 pi. So the only reason the period changed is because we had a function transformation. Moving on to the cotangent function. The graph is very similar to the graph of tangent, and it also has a period of pi. However, from the identity, tangent we know is equal to sine over cosine, and we know that cotangent is the reciprocal of tangent. So in other words, it's the reciprocal of sine over cosine, so that's why we have cosine on the numerator, sine on the denominator. This function is also odd, and it will also have vertical asymptotes, not at negative pi over 2 and pi over 2, but they will be at multiples of pi. And let's see why. So anytime, so cotangent is undefined. Anytime if, let's say, if sine of x is equal to 0, right? Because if we have a 0 on the denominator, we cannot divide, so therefore we say it is undefined. So that will occur based on our unit circle, that will occur here at this point. The coordinates are 1, 0. Remember, sine is, it's going to be here, this one. And also at this other point, which is pi. And the coordinates there are negative 1, 0. So sine is this y value here with respect to the unit circle. So at those 2 points, it will be undefined. And so your consecutive vertical asymptotes, one to the left, one to the right of the y-axis, and they would be located at negative pi on the left and at positive pi on the right. And those are for your vertical asymptotes. The graph of the cotangent function, it is similar in shape to the tangent function, but just as a quick reminder, the tangent function, the curves between the asymptotes, they are increasing if we read them from left to right, which we all should. And the graphs from the curves from the cotangent function, they are decreasing if you read them from left to right. So that would be one of the main differences. Also that the period, well, no, the period, it is the same, pi, but another difference is that the asymptotes will occur at 0 and at pi. And we could see those here. This one's not really marked because it's the y-axis, but here's the other one at 0 and at pi. And the x-intercept, instead of being at the origin, it is at pi over 2, because the cotangent at pi over 2, right here, cotangent is cosine over sine, and that will be cotangent of pi over 2 will equal to cosine is 0 divided by 1, so that is equal to 0. And so that's why the x-intercept happens there. The vertical asymptotes will be all the multiples of pi. So we're going to have pi, negative pi, 2 pi, negative 2 pi, 3 pi, negative 2 pi, and so on. So because those are the vertical asymptotes, we have to exclude those from the domain, and that's why we use the does not equal. So x could be any angle measurement, but not any multiple of pi, whether it's negative or positive, or even 0 times pi, which is be 0, and that would be the y-axis that is also serving as a vertical asymptote. For the next question, we're going to go ahead and graph transformation. So the first two equations, just to refresh our mind, when we were graphing tangent, we were taking what was the input for the tangent function, and we were creating two equations and equaling one to negative 2 pi over 2, and the other one, remember this is for tangent, to positive pi over 2. For cotangent, we're also going to create two equations, but instead of using those two values, we're going to equal 1 to 0 and 1 to pi, and the reason is because those are the vertical asymptotes. The y-axis, which is the line x equals 0, that's why we equal this to 0, and this is for a vertical line, not for an actual x value. And the other one will occur at pi, and those are for the parent function. Remember, this is a transformation. So when we solve this equation, we're going to get 3 is dividing the x, so if we take the 3 across, we will be multiplying, so it will be 3 times 0, which it will just be equal to 0. For our other equation, we're going to have x is equal to 3 times pi, and that will be the other vertical asymptote. So we have our two vertical asymptotes. One will be here, the line x equals 0, and the other one will be here, x equals 3 pi. And because the period, well, no, let's just leave it right there. The period for this one, just because we had a transformation, we had that 3 dividing the x, the period changes from pi to 3 pi. And you could always find out what the period is by calculating the distance between two consecutive asymptotes. So if you go from 0 to 3 pi, that's why I'm saying the period is 3 pi. So everything will still repeat for every 3 pi radians. So let's look at the table that we have here. And if we were to substitute, or actually, let's do the following. We found the two asymptotes, and we know that they're asymptotes because the value is undefined at x equals 0 and at x equals 3 pi. So to find the x-intercept, we're going to calculate the midpoint between the two asymptotes. So to find that x-intercept, so we're going to take 0 plus 3 pi and divide it by 2, and so that will be 3 pi over 2. And so that's how we get the x-intercept that you guys see right there. So at 3 pi over 2, if we were to substitute it into this x, it will be equal to 0, and so that will be an x-intercept. Now it's a good idea to get another 2 points. Remember, we were talking about key points. So of course the x-intercept is one of them. The asymptotes, even though they're not points, they're still key. Consider key values, I guess. And then we're going to need another 2, and those 2 are going to come from that one that I just highlighted is going to be the midpoint between between 0 and 3 pi over 2. So to find that midpoint, it will be 0 plus 3 pi over 2, and then divided by 2. So this will be 3 pi over 2 divided by 2. So think about 1/2, and if you divide it again by 2, you actually get a quarter. So this will be 3/4. And that's why we have this value here. And if we were to substitute that into the cotangent function, let's do it over here. So if we have 2 times the cotangent of, and what are we substituting? 3 pi over 4. 3 pi over 4, but we're still dividing by 3 here. And so that will be the same as 2 times the cotangent of, remember this has a 1, so it will be 3 pi over 12. And if we simplify this, it will be 2 times the cotangent of 3 pi divided by 3 is pi. 12 divided by 3 is 4. And so this is another easy one because the cotangent of pi over 4 is 1. So this value right here is equal to 1. And so 2 times 1 is 2. That's how we get this 2 here. And so that is that other key point. And then finally, to find this one, the 9 pi over 4, first we will take the midpoint between 3 pi, the asymptote, and the x-intercept. And so for that, we will have 3 pi over 2 plus 3 pi divided by 2. And so 3 pi in halves will be 6 pi over 2. We're dividing everything by 2. And so this will be 9 pi over 2 divided by 2. So it will be equal to 9 pi over 4. And that's the value that we have here. And if we were to substitute that into our original function, which is the cotangent, if we were to substitute it where this x is, I'm not going to do it to not make this video so long, but the result for that will equal to -2. If you type this in your calculator, make sure you do use parentheses accordingly. And also the pi symbol, make sure that you type it in radians. Okay, from here, we get the point that will go here. The x value is 9 pi over 4, the y value is -2. And so with those 3 points, we could trace our curve. You could see that they are decreasing, and you could see that we have asymptotes as well every 3 pi radians. You can obtain the graphs of the 2 remaining trigonometric functions, which are the reciprocal functions. And those will be the reciprocal functions of sine and cosine. So the reciprocal of sine is going to be cosecant, and the reciprocal of cosine is going to be secant. And so to graph those two, cosecant and secant, we actually need to graph sine and cosine. So that is what we cover on the last section, 4.5. So this should be a little easier. And of course, whenever the sine function, if sine of x is equal to 0, then the cosecant of x is undefined, because we cannot allow ourselves to have a 0 in the denominator. And of course, similarly, if the cosine is equal to 0, then the reciprocal doesn't exist. So if cosine of x is equal to 0, then secant of x is undefined as well. And so we'll see on the next slide where that will be happening. Okay, and this is just, we're going over again how when the cosine, just to reinforce this, whenever cosine is 0, if cosine is 0, tangent and secant is undefined. So because there are values that we exclude from the we exclude those values from the domain, which are pi over 2, negative pi over 2, negative 3 pi over 2, 3 pi over 2. What happens is that they are also going to be vertical asymptotes happening at those particular values. So remember, just like we had at pi over 2, and then every pi units after that. So just like that, for cotangent and cosecant, so if sine is equal to 0, then we know that cosecant and cotangent are undefined, and moreover, they will also have vertical asymptotes at those particular values. And I remember that sine of 0 equals 0, and so does sine of pi equals 0, and of course also sine of 2 pi will equal to 0, and also for negative angles. So at those angles, 0, pi, and pi over 2, since the sine is equal to 0, that means that cosecant is undefined, and in fact so is cotangent. Similarly, cosine is equal to 0 at pi over 2. It is also equal to 0 at 3 pi over 2. And it's also equal to 0 if we want to go in the negative direction at negative pi over 2, and so on. So at those particular values, that will cause tangent and cosecant and secant be divided by 0. So we do say that they are also undefined at those values. To sketch the graph of a secant or cosecant function, you should first make a sketch of its reciprocal function. For instance, to sketch the graph of y equals cosecant of x, first we will be graphing y equals sine of x. So right here is the parent function of sine of x. And after you do that, what happens here is that whenever your sine function is equal to 0, which is actually where it touches the x-intercept, at those same points, you are going to have, for the reciprocal function, which is cosecant, and is what I'm highlighting in yellow, in between those curves, where the x-intercepts are for sine, you're going to have vertical asymptotes for cosecant. And you could see those dashed lines. Those are the vertical asymptotes, including the y-axis. So what is the period of cosecant? The same as sine, 2 pi. And you could see that they repeat every 2 pi units. Also, the domain will be all real numbers, almost like sine, except where we have asymptotes. In this case, they will be the numbers that we have to exclude, and those will be the multiples of pi. What is the range of this function, the y values? What could it be? Well, if you look at the point that I'm about to trace, let's say right here. Well, remember the range of sine. For sine, the range is from -1 to 1. So that means that this maximum point has the coordinate of 1, the y coordinate, and this minimum point on the graph in purple, okay, it has also, not also, but a -1 for the y value. So those are, that's our range for y values. Our y values are between those two numbers. Now, if you look at the graph that I have highlighted in yellow, the range or the y values could be any number that is either greater than 1 or smaller than -1, but not the ones in between. So how do we exclude those? So we use the union of two intervals. And so what we're saying here is that the numbers could be very small, but then they will stop at -1. We do include -1, that's why we have the square bracket. And then we leave that little gap in between, which is, I'll point it out here. So that gap will be kind of like from here to here. We leave that gap. This is the gap of the y values that we want to exclude for the range. And so we do that, and that's why we use, again, the square bracket, but we jump to +1. So that is telling me that whatever was in between -1 and 1, it's already out of the question, is excluded. And remember, with negative infinity and positive infinity, you always use regular parentheses. Okay, where are the vertical asymptotes going to be at? They're going to be at multiples of pi. Because at those values, the sign is equal to 0. Like at 0, at pi, at 2 pi, at 3 pi, 4 pi, and also -pi, -2 pi, -3 pi, and so on. Okay, so the actual graph of cosecant is just what I have highlighted in yellow. That's the only thing you will see on your calculator if you were to graph it. And the asymptotes, you might not see them on your calculator, but on WebAssign, you might still have to graph them. So you have to learn how to find them. Okay, now let's look at the secant function. And so, of course, we already established the secant is the reciprocal of cosine. So what I'm going to do is graph cosine with blue. I'm going to highlight it. And remember, this is from last section. And now anywhere the cosine is equal to 0, which happens at pi/2 and also at 3 pi/2, or also at -pi/2, and so on, those will be your vertical asymptotes for the graph of secant. So secant is what I'm highlighting in green. That's the graph of secant. And then let's go ahead and trace the asymptotes. You already can see them there, but I'm going to highlight them with pink. Remember, if you graph this on WebAssign, you might have to make those asymptotes dashed lines or dotted, depending on the option. So those vertical asymptotes is what we actually exclude from the domain. So that's why we have does not equal to. And those also repeat. They start at pi/2, and then you keep adding pi. And that's what will give you your asymptotes. Similar to cosecant, the range is all real numbers. Also, I want to point out that here we have arrows like that, but the graph doesn't touch the asymptotes. And so it could be any y value, it doesn't matter how small or how large, except for the numbers in between -1 and 1. We exclude those. So to exclude that, we use the union symbol that we have here, and we break our interval into two. So it's similar to if that was your number line, this is 0, this is -1, and this is +1. So we want to take everything from here to here and from here to here. So that's why we have to use the square bracket. So we still include -1 and +1. And of course, we take from -infinity to -1, union from 1 to +infinity. And that's how we get the range. Also, cosecant is an even function. And so that's why it is symmetric with respect to the y-axis. Another thing I forgot to mention for cosecant, it is an odd function. Odd function, just like sine. And because of that, is symmetric with respect to the origin. So this book likes to use the terms hills and valleys. I personally prefer minimum or maximum. And so what we're gonna go over on this slide here is that whenever your sine function has a maximum point, such as the one here, it's a maximum for sine, but for cosecant is actually a relative minimum. And we say relative because first of all, it's just in this interval. It's not the minimum of the whole function. And since this function goes all the way to -infinity, well, from the range it starts at -infinity, we do not have a minimum. We could all find a relative minimum. So similarly, if your sine function has a minimum, remember sine function is highlighted in blue, that will be the sine minimum. So it will also be the cosecant relative maximum. So that's another thing that it is important. Let's move on to example 4, and we're going to sketch the graph of 2 times cosecant of x plus pi over 4. So the 2, it's going to change. Well, first of all, we're going to begin by sketching the graph of the reciprocal of cosecant, which is sine, but we will have all the same numbers or constants there. So the amplitude for sine is going to be a 2. It's going to be like a vertical stretch. And the period here, because the coefficient here of the x is a 1, it doesn't change. It's just 2 pi or 2 pi over 1, which is 2 pi. And what we have here is a phase shift or a horizontal shift or a horizontal translation. And remember we said we were going to find our starting and ending point for one period by setting up 2 equations with whatever was inside the parentheses here. So that will be x plus pi over 4. One of those will be equal to 0, and the other one will be equal to 2 pi. So to solve for this one's first, here the pi over 4 is adding, so if we move it across, it will be subtracting, like that. And for the other one, we will have x is equal to 2 pi minus pi over 4. 2 pi converted into fourths is 8 pi over 4. And if we subtract pi over 4, and this is going to give us 7 pi over 4. So that will be based on this phase shift. One complete period will start at negative pi over 4 and it will finish at 7 pi over 4. And in fact, that is because this pi over 4, it made the graph, the parent function, move not x, but pi over 4 units to the left. That is what occurred. And so we have here also two of our key points. Since we're graphing sine, those two are gonna actually happen to be x-intercepts, both of them. So let's do that on the next slide. And we could see them here at negative pi over 4. It will be here. And the other one was at 7 pi over 4. So that will be there. And remember in fact, that is not 7 pi over 4. Sorry. 7 pi over 4 is right here. So those are the 2 points that we needed. Now, one complete cycle of sine will start here, and then it will end there. Now, how do we find the exact x-intercept in between them? Remember, we had a little trick for that, and it's all about finding midpoints. So if we have negative pi over 4 and we add the 7 pi over 4, we will get 6 pi over 4. And remember, we're going to take the half point, so we're going to eventually divide by 2. So first, let's simplify 6 pi over 4. That will equal to 3 pi over 2. And then dividing by 2, that will be 3 pi over 4. And that will be our other x-intercept, which is right there. So this is also another x-intercept. Okay, to find the maximum, which will go here, we're going to find the midpoint between those two x-intercepts. So it will be negative pi over 4 plus 3 pi over 4. And we're going to divide that by 2, of course. So that will be 2 pi over 4 divided by 2. And this will equal to pi over 2 divided by 2. So it is pi over 4. And that is the value that will actually go here. Pi over 4. Okay, now let's find the minimum point for the sine function, and that will be located right there. So let's do that, and that we'll find it by calculating the midpoint between this x-intercept and the other one. So the one on the left, I believe is 3 pi over 4. And midpoints, remember, we're adding, dividing by 2. The other one is 7 pi over 4, and we're going to divide by 2. So with that one, it will be 10 pi over 4 divided by 2. And I feel like I need to check something. Okay, so we were right. We take the 3 pi over 4, that was 3 pi over 4. This is 7 pi over 4. We add them, divide by 2. So we have 10 pi over 4, which is reduced into 5 pi over 2. But we're still dividing by 2. And so this will turn into 5 pi over 4. And so that is the actual number that the x value for which the y value is equal to -2 in this case, because the amplitude is 2. So this is positive 5 pi over 4. And that's where the minimum for the sine function occurs. Okay, so now that we have traced that, whenever we are looking for the graph of cosecant, not of sine. So whenever we have x-intercepts, those will turn into asymptotes for the actual cosecant function. And we could extend our sine function by repeating everything every 2 pi. That is the period for this one. And simply what you do at the end, this is what the actual graph of cosecant is. It will be what I'm about to highlight in green. So if we see a point here that is like a mountain for the sine function, it will be a valley for the cosecant. In other words, if it's a maximum for the sine, it will be a relative minimum for the cosecant. Now here we have a minimum for sine, so we have a relative maximum for cosecant. And we also repeat that for as many periods as we need to. Also, you could use your calculator to check your work. There's nothing wrong with that. Just make sure you do use radians. You must use radians on your calculator. So you have to go where it says mode and make sure it does say radians or has the word radians highlighted. Okay, the next functions here are called damped trigonometric functions or graphs, and those are the product of two functions. And what we do is we graph them using the properties of both. Now, I'm not gonna explain the long way of this too, but I'll give you the short version that this graph is gonna be somehow bounded by these two linear functions, which are y equals x and y equals negative x. And so we have the graph here on the next slide. And you can see those two lines that I was mentioning. These are not part of the graph. They're just telling you how the graph will be bounded or kind of like restricted to. So for a function like this, I will just prefer that you graph it with your calculator, you get some key points, and then you complete your assignment. I don't really see myself giving you a function like this on your exam, but you never know. So if we were to use this, you put it on your calculator, you look at the table of values, and then you plot some points. And so the actual graph for this equation is going to be, and this is the equation, it will be the curve that we see here. And you could see that it is oscillating, but it is in between those two linear functions. So if we were going to extend it, perhaps, it will continue to do that in both directions. Okay, not the best graph. Okay, so similarly here we have that e to the power x times sine of x. So we call this the product of two functions because even though you don't see a multiplication symbol, this is one function, this is the other function. So the e to the x, or actually e to the negative x, it's right here. And if we use a reflection of it across the x-axis, we will get this graph here. So what happens is that the function sine of 3x, it will be in between those two other functions. So let's say for this one, it will be this curve, and so on. So again, something like this, I will prefer you use your calculator. So you will enter it, you find the button that has the e to the power x, and then in this case it's negative. So once the exponent or the caret symbol appears, make sure you use the negative sign that is at the bottom of your keyboard, and it's inside parentheses. You need to use that whenever it's at the beginning of a variable or a number, not in between. And so you use that, then you put your x, Then you need to use your right arrow to get out of the exponent. Then you look for your key that contains sign, and then in parentheses you will enter 3x. So let's just go ahead and graph it together. So we press y equals. Now the button that contains e to the x is actually in blue. I want you to find number 4. Look on the left side, and we see the letters ln, that's for natural log. And in blue, we see e to the power x. So we have to press the second key and then the ln key, and that will bring the e to the power x. In this case, I don't have the caret symbol. Instead, I have that box that is blinking. So I'm going to use the negative sign, the one below number 3. And then I'm going to enter the variable x, which is on the top, second column. Now, what I was saying is, you see how the thing is blinking next to the x. So I don't want to keep typing inside the exponent, so I'm going to use my right side arrow. Then I'm going to enter what we were supposed to enter. I forgot. And it is sine of 3x. So sine, it has its own key. And then we enter 3. And then we enter x. And then parentheses. Now I'm going to go back to the main screen, make sure I am in radians. So I'm going to type second and quit. And then here I'm going to press mode. And you could see that I am not in radians. So I'm going to use my arrow and make sure I highlight. I'm going to press enter where radian is blinking. You could see it now highlighted. Now I'm going to go back to the y equals, and now I can graph the function. So I'm going to press enter, and let's, on the top buttons below the screen, the one on the right says graph, and there we have it. And I know it does not look much like our picture, but remember, it is doing that oscillating behavior. And so that's how it will look. And if you need to look at the table, would you see the button that says graph is in red? In blue it says table. So if I press second and then graph or table, you could see the values there. And so this could be helpful when you're graphing your something like that. So just to finish, here's a summary of the graphs that we've been studying. So we have sine, cosine, tangent, cotangent, cosecant, and secant. And as you can see here, we have secant and cosecant without sine and cosine. So those are the only part of the graphs, the ones that look like parabolas. So this is our last slide, end of the video.